This is the last talk of today. So I'm both happy and kind of nervous. Happy because surrounded by friends and students and colleague mathematicians, and nervous because of poor math, poor English, maybe poor life. Okay, so nobody laugh. So today I'm talking about the Keller-Segel equation, and it's from biology. So, okay, so there is amoeba called this name. Yeah, and so I found some people called this amoeba by dictee. And the amoeba live in the soil, and the amoeba is chemotaxis, meaning that chemotaxis. When people say chemotaxis, then here taxis means response toward or against the external stimulation, and chemo, what stimulation is. So if the amoeba towards or against some chemical, then it is chemotaxis. Other example is aerotaxis, and it means that organism act towards or against air, actually oxygen. So aero means air. And other organism called phototoxis. And as you imagine, it's act toward or against light. Okay. So this amoeba has act towards some chemical. Okay. So what makes interest is that normally, if food is abundant, this amoeba live in a unicellular. But after the food supply is short, then they congregate and move into different stage and differentiate two types of cells. So the life cycle for this amoeba maybe draw like this is unicellular amoebas, and they are big as 5 micrometer. And food supply is short, then they produce some chemical called CAMP, and due to this chemical, they aggregate each other and make some collective body, and then they make other stage of life. Then finally, they differentiate two types of cell. So this one is unicellular, but those are multicellular, and then it's called a fruit body. And they release a mature spore to be this stage again. And the Keller-Segel equation describes this stage. So in this equation, people derive this equation by understanding of extracellular mechanism. So I mean intracellular mechanism. Maybe this is a matter of real biology or chemistry, or nowadays even quantum mechanics, because molecular size or atomic size is really small. So nowadays biologists talk about quantum mechanics really act. But this equation, so for this equation, we deal this amoeba macroscopic way. It's just so I cannot imagine we deal with many particle systems, something like that. So you just consider the population density at one time, at one place, and leads to a reaction diffusion equation. So what equation is that? So mass conservation leads this equation. So we have flux here, and this is unit out or unit normal. And for chemical, so this chemical produced by amoeba itself, they are not conserved, they produced. So we have the producing term, let's say Q, the X, and the flux term. And so one assumption is that amoeba and chemical diffuse. So this flux term includes some gradient of N and gradient of C. So we arrived at, okay, so N. And the observation is that they aggregate toward the high concentration of chemicals. So people put here like this term per density, and here it's just to diffuse, and here Q is produced by bacteria, amoebas. So some parameter times N. This makes the simplest model for Keller-Segel equation. So if you write the pointwise sense, the equation is and this. Okay, let's just ignore now. Okay, wait, guys. Okay, but those plus. So this parameter function is called the chemical sensitivity function, and this is called maybe some it's called production function. I see. Okay. Okay. Well, and the same mechanism explains the aerotaxis, but for aerotaxis, now the chemical replaced with oxygen, and amoebas consume oxygen. It means it should change this sign plus to minus. So here we put minus, okay, yes, minus for aerotaxis. Okay, and normally people couple this equation with Navier-Stokes or other Stokes or some kind of fluid equation, because aerotactical organisms normally often live in the water. So here we may put the drift term by fluid, incompressible fluid, here and here, and since we think incompressible fluid, okay. This is a potential for external force. Okay, but in this lecture, I ignore the effect of fluid. Total ignore, and this and this. Actually, after some computations or after some experience of the equations, the fluid just fluid does not make new difficulty, nor they make the equation simpler, except one case. I will explain that later. So, okay, for simplicity, we just ignore the effect of fluid and start with the Keller-Segel equation for simplistic case. And originally, Keller-Segel equation for C does not have this time part. In that case, original Keller-Segel equation written by and chemotactic case. And it is well known that, okay, and now for this lecture, I will only consider two-dimensional case. Maybe it is most physical and simple in embedding sense. Okay, and R2, and it is well known that if initial data is bigger than some amount, then the classical solution does not. Classical solution should blow up. So I don't know exactly literature, but certainly this paper by Herrero and Velázquez in 1997, one of the paper considering the blow up of this equation in R2. So in this lecture, I would like to show how much we get by integration by part. So I would like to show the blow-up mechanism because it is simple and it has some similarity with things where Zhuizhang's talks appeared. Okay, so they think.
In this case, the blow-up is mass concentration.
Yes, you will see. So they consider this quantity, x squared R2 times n, and time differentiation gives z. So plug the equation. Okay, and this paper or the paper to show blow up, they just to put chemical sensitivity function constant. Let's say 1. Okay, and then by integration by part twice, 4 times n, and this kind of equation, the mass conservation law holds. So it means n at one norm of n conserved. And C, for this equation, C, well, okay, the error taxis, because of the minus term, we could estimate all the LQ norm of C bounded by initial amount. Okay. Then, let's see. The 2x, this minus 2x, okay, the 2. So I put 1, x dot n gradient C. And they put the formula for negative Laplacian of C equals, okay, they put here just to, not k of C, the n. So all the parameters are constants in this case. Then, I'm sorry. Then we know that minus Laplace inverse of n is C, which is fundamental solution in 2 dimensions. Okay. Well. And then gradient of C and n y t y. Okay, and we have this one. So you see, we have 4 times the L1 normal initial data, and okay, the minus the plus 2. Okay.
So you're assuming that N is positive, right?
Yeah.
But the C is not necessarily positive.
Oh, C is positive. C is the amount of, C is chemical concentration. So she should be positive or 0.
But from that formula, it's not clear if C is positive.
Yeah, actually, oh yeah, you're right. You're right. Yeah. Yeah, maybe it's for. Let's go. Yeah. Okay. And then we arrived at this is okay. The we need the plus 2 times x dot n and gradient c minus 2 pi, and here x minus y, x minus y square, then ny dy dx. So you see this part actually, so we see that this is that y, if we change x and y minus x and x dx dy. Okay, and then minus x minus y. So this integral called a, then 2 times, okay, yes, yeah, times y makes x and y, and in this way we get here square. So a is that. Okay. So it means we start from this differentiation, derivative of this positive norm arrives at 4 times L1 and negative 2 pi square L1. Oh, sorry. So we see that 4, 1. So now this L1 norm of initial data appears the critical quantity. So it's 8 pi. If I have the parameter chi here, then this quantity is 8 pi over chi. But here 1, then it turns out that the solution globally exists, but this quantity is bigger than 8 pi, then apparently the small solution, if the initial data has this weighted norm bounded, then classical solution doesn't exist longer. But this argument fails when we have minus sign here. So actually, as far as I know, so this is the parabolic elliptic Keller-Segel equation in 2 dimensions, and they blow up. But what happened? I put here this term, then I don't know. Maybe there is a result where the solution blow up. but it's not clear. So I think there is no clear evidence of blow-off for this parabolic Keller-Segel equation, even the this chemotaxis case plus case. But when we have minus sign here, then as I told you before, we have other global estimate in terms of C, because just integration by part, so multiply c to the q minus 1 and integration by part leads that every LQ norm of C bounded by C L0. So this Q can be infinite. So this is a really good part of the aerotaxis equation. So we hope that at least 2 dimension we may have global classical solution, but it turns out that we don't have yet. So I try to show what conditions we have for solution to exist globally, and in what case we can have global solution. So, okay. Before going,
you call that a maximum principle?
Maximum principle in terms of size of C, but it doesn't help much. Actually, we need a little bit more regularity. If C is wider, then solution globally exists globally, but we don't know that. Actually, that makes the part of regularity criterion for 2 dimension. That part. Okay. Before going further, I would like to introduce other model called angiogenesis. Angiogenesis meaning making new blood vessel for cancer tissue. So the biological situation a bit different, but in this, the reaction diffusion equation explains that case also. So few days ago, I read some article linked in my Facebook page, and it says that 2000 Cell, the prominent journal Cell, there was an article highly viewed and really shared by many people, and the author is some famous person, but I don't know. And he says the 6 hallmarks for cancer cell are: they can grow without growing signal, grow, and they don't stop their growth. And they ignore the message to say now is time to die. So they ignore so people call that message apoptosis. Ignore apoptosis message. And fourth is they just to replicate forever. Limitlessly. And the final 2 hallmark is that they have ability to make new blood vessel. It produces the nutrition toward them, called angiogenesis. And the last one is that metastasis. the final stage of cancer, the cancer stage can move to very distant organ, and almost always people die of that cancer, not because of the primary cancer. So, okay, so this angiogenesis is, well, described by the Keller-Segel equation as well. So, because I don't know biology yet much, but I try as far as I can. Okay, there is a tissue by cancer tissue, and they are very bad, right? And so the oxygen concentration very low, and they trigger some protein called what's that? Okay, they trigger the cells to increase their concentration of a protein called H1F1, and this stimulate other protein called this, and this is nothing but the vascular endothelial cell, the growth factor, which appears as C in our equation. This appears as C, and this vascular endothelial cell is just a cell lining our blood vessel. So the blood going back from forth, then this cell lining this lumen, and here the lining of vascular endothelial cell. So the picture is that if there is cancer tissue and they are lack of oxygen, and they produce the chemical called the protein called VEGF, and they diffuse this protein, and there is a blood vessel far away, not far away, I don't know, and they act toward this protein, and new capillary blood vessel grows. So the density of endothelial cell appears as N, this equation. And they do not consume this protein, as is the irotactic case, but the protein, sometimes later, protein just disappear from this picture. So we put the minus sign here. Yeah. So the irotactic equation both describe the irotactic situation and angiogenesis situation. And normally, these two parameters determined by some experiment. So this equation is kind of phenomenological equation, I think. So mathematicians like the condition of continuity, and they like to assign the spatial sign. So many mathematicians put the condition of those parameters are non-negative, and they are increased, and of course 0, and some continuity, and maybe C1 or C2, some regularity. Okay, but actually, other in papers written by biologists, they like the condition of this chi of C is reciprocal of C, and actually in some experiment shows instead of this, put this. So in angiogenesis case, people usually use those. I mean, the chemotaxis sensitivity is reciprocal of C, and this is gradient of log C. So when people use those the chemical sensitivity function, then it's called sometimes logistic Keller-Segel equation. So what good feature of the logistic Keller-Segel equation is that they have some traveling wave solution. So if I write down the logistic Keller-Segel equation, N C N in simplistic case, we put here C, and it's 2 or 3, 1 or okay. For angiogenesis case, the one-dimensional model is quite realistic because the blood vessel is quite thin and long. But also in thinking of the feature of the cylindrical blood vessel, so we often think about the cylindrical domain, I mean the infinite strip domain with cylindrical boundary condition. Anyway, R1 or R1 cross strip with periodic boundary condition. And then for this logistic equation, Kohl-Hopf transform is really important. So Kohl-Hopf transform, Hopf-Kohl transformation is that, what is Kohl-Hopf transformation? That we use the new variable instead of C. And then we can rewrite the equation in terms of N and Q. So C is a scalar, is concentration of some chemical or something, but here Q is a vector variable. So if I use this Q, then the equation, okay, let's put epsilon here. Then the equation, change it by NQ. And somewhere I use the curl-free condition of Q because of this Q is gradient of some potential, then Q equals 0. At some point, I should use that condition to derive those equations. Okay, so when epsilon is negligible, I mean the diffusion of a chemical or something is negligible, then just we draw these two terms, and then really we get some hyperbolic conservation law. Yeah. So it's just to we can expect the global solution of the conservation law 2 dimension. So if I put here this logistic term, then it turns out that the equation is a partially dissipative conservation law. Then the equation allow for the small data global solution. So my recent work was about actually for the traveling wave, stability of traveling wave, or this partially conservative, partially dissipative hyperbolic law. But in this lecture, I would like to introduce a basic result, the regularity criterion for quasi-problem. Okay, so well, for the study of traveling wave solution or that the dissipative conservation law, that Kohl-Hopf transformation is really important. Otherwise, I cannot have the global solution here. Okay. For expert here, I can use Kawashima's compensating function. Yeah, the Kawashima compensating function appears in the study of that equation. As long as I put that the logistic. Okay. Of course, in that case, I expect that and near 1, the equilibrium point. So if the initial density is very close to constant state 1, then the solution stay around 1 forever. Okay. Okay, let's move. Well, now okay, here. So what's wrong with the chemotaxis equation? Why cannot we have global solution? It seems too good quantity preserved. Okay, here. So we always put the condition of that there on chi and k. So if we assume those quantity, what's that? I should say if I further those conditions, then there is an energy conservation. We can find some kind of energy conservation. Actually, it's better to call the entropy inequality, entropy equality, if we assume those conditions. But as I told you, this chi and k determined by some experiment. So some people think it's too much to assume the second derivative, the sign of second derivative, and I cannot find any true meaning of this condition. But anyway, if we assume this condition, and there is some very complicated but nice inequality, found by some Russians, and Winkler used this inequality to show the solution exists globally in 2D bounded domain. Normal boundary condition, the solution exists globally. But without that condition, then the mysterious inequality doesn't hold any longer. So we just do integration by part, and with some good quantity appear. So let's see. Okay. So, okay, let's start from L2. So multiply n and integration by part, and I get and always these two are bounded by some constant times L infinity norm of C, and C have very good estimate for all Q. So we always this size or this size by constant with respect to C0. Okay. And so we have here the gradient of C. So we multiply Laplace C and integration by part, then okay. From these two equations, we easily see if we have the L1, L2 norm of n finite, then this inequality closed by Groner equality. Actually, this solves the blower criterion. So for any t, then the maximal existence time interval is infinite. And if you perform the higher order integration by part, then as long as we have these quantities bounded for any t, then the higher order estimate easily closed. So this serves the blower criterion. Okay. Okay. Then it's okay. Yeah. So, but well, in the first equation, if you temporarily put this q minus, okay, just q, then we see the equation is that this term should be minus minus plus qn. So it's just the first equation of some hyperbolic conservation law. So we're mimicking entropy and the entropy flux pair method in that equations. What we find is that if we n log n, so if we differentiate that quantity and we have some inequality, let's see, the nt, so 1 plus log n, and nt, so we have negative qn plus, and integration by part, several integration by part, we arrive at, and we always have the nice inequality for gradient c. N. Okay, q. Okay, q. And then okay, let's see the gradient. So, n, gradient n. Q is this n plus what? Okay, this is gradient n. That plus gradient n. Okay, and I think here we have some, here minus sign, it should be minus sign. And then the summing those two equations, we arrive at and this makes this particular term, and then we have chi of c and c, and if we integration by part toward n, then we have chi of c. Okay, so this term, we can see this term by the gradient of square root n, L2 norm. And for this, k, n, C. Okay, for now, just to ignore the negative part of log n, then if we have the smallness of this quantity, then the inequality is closed by Groner inequality. So actually, we could put the parameter here, multiply mu for some constant, then we still have those inequality, mu, and here, mu. Okay, and so the subalpha embedding, by subalpha embedding, we have this bounded by this and gradient this, and this is nothing but the L1 norm of n, which is preserved L1, and here we have the supportive part for this term, and this is L2. There. So we just see where the that in 2 dimension we have that the regularity criterion is that this L1, L2 norm bounded, then the solution exists globally. And here, if we somehow, able to the negative part of n log n, then we could estimate L2 norm of n by the supportive term and L1 conservation. And this this negativity issue is typical in kinetic community. So actually, in Boltzmann equations and on other kinetic equations, this f log f, they called entropy, real entropy, and here the way of dealing of log f, just to the domain, decomposed domain. Let's see the domain where n less than 1, and here we decompose the domain into the minus x square and complements. So in this way, we can estimate by n log n negative some constant plus n, and this multiplied by this weight. And where is this weight from? Because we take the logarithmic of this function, then we have some weight x. And this equation allows us to estimate this quantity by all quantities appearing here. So in this way, if the sensitivity function satisfies the relation like so in 2D, we just observed that if our sensitivity function is satisfy the smallest condition, then the global solution exists. And actually, for the aerotactic equation, there is some paper by Tuvar and his collaborator, and they put their parameter, the Heaviside function. So there are some sister, and just to their parameter function satisfy actually 0. So and actually we can foresee this energy estimate in 3-dimensional case, and there it turns out that if this procedure can be closed, then we really need this relation. It seems too much. in 3 dimension. Okay. But in 3 dimension, there is another argument. If following that argument, we could show that if we start the small C0, then the solution exists globally. Okay. And this condition is different from smallness of C. So one example of initial conditions to satisfy those conditions is, of course, we put the very small C. Then everything is small. We don't need subtract this amount, that amount, just to see if C is small, then everything is small and still small. So this is one example. Okay, but actually, this condition says we don't need smallness. It's just to satisfy those inequality. And the other easy observation is that however large chi of C and K of C is as constant, however large, but they certainly satisfy those relations because okay, make exact zero. So constant parameters satisfy those example, and small initial data also give us that relation hold. So we want to find a new regularity criterion to make connection with those observations. So what we thought is that okay, constant parameter will be okay. Then we just think and this. Okay. And also for K, and then so we decompose this parameter function like obvious way, this obvious way, and then 2 parts, and the constant part will be okay. And if we have some continuity, not continuity, continuity is a bit short. The regularity in C and chi is always continuous or regular. Then also we need some local version of regularity criterion. Then we might be close this observation to drive other regularity criterion. It does not mean we have global solution. Just to we can find another regularity criterion. Okay, what's that? We can show that. So, yeah, okay. So we found that if the C satisfies those conditions, and here Q is parabolic cylinder, and G is space-time, X and T. Yes. That's the center at X and radius of R times some T minus R square T. So if for any G, okay, less T0 is maximal existence time, And for any t, for any g, which time is less than t0, if there exists uniform r and epsilon 0 such that those inequality hold. So actually it serves the new Broad criterion, and we can show that as you can see with this condition we can somehow make this trick work. So if this condition true, then we can show the n0, n square is uniformly bounded by some epsilon and r, which is rho is any rho less than r. Then in this lecture, we observed many times this L2 quantity, space in time, really essential to make energy estimate close. So what we did is multiply some cutoff function and then proceed energy inequality, energy estimate, and locally. So we can show that and see. Any LP is bounded, and with this we use the parabolic embedding gives us that with this inequality actually N and C is Felder. And then, so if we assume this condition, then the locally spacetime L2 is bounded, and it allows us close this energy estimate, and we get N and C is locally uniformly Felder, and then we have always L1 conservation. Then we could derive some contradiction if the maximum existence time is finite. Then it leads on contradiction. So that's, and the other way is easy. So this is the criterion we have, and actually this broad criterion is equivalent to have the spacetime L2 norm of n is bounded. Okay, and certainly if C is small, then everything is small, so we easily pass this condition. Yes. Do I have some time?
Oh, yeah, sure.
The final topic is that since this L2, the spacetime L2 norm n is really essential, but we cannot show this quantity is bounded with just this broad criterion. But a few years ago, the Kiselev and his students published a very interesting paper dealing with the suppression of chemotaxis blow-up by fast incompressible fluid. So this is not my result, but I'm really interested in that paper. There they really use the drift term, but their drift term by incompressible fluid is not, their fluid is just a given fluid, not fluid of Navier-Stokes or Euler equation. They just give some fluid with some characteristic, and it really suppresses the blow up of chemotaxis equation. So in 5 minutes, I would like to introduce their result. Because actually, their result is the application of the study of how drift term affect the diffusion in compact Riemannian manifold. And the Konstantin Kizalev, Reisnik, Zelatos published some paper 2005 in Annals. And there they studied some reaction enhancing flow. And this paper by Kizalev Su apply their result, those result in Annals paper to the specific case. So they consider the classical Keller-Segel equation with some input term n u n minus they use kappa constant c gradient c n, and here they use parabolic elliptic equation n in torus, and b is 2 or 3. Because of subalipin embedding, their result cannot apply the higher dimension. This is also interesting point. Okay, and so what they here, sorry, put here. What they proved that if U is a weakly mixing flow, then the solution is exists globally. Here, A. So the precise theorem would be U is weakly mixing flow, weakly mixing flow, and they did not state explicitly, but their vector field is autonomous, meaning time independent. So autonomous. Then actually for any initial data, smooth initial data, exists weakly mixing flow such that A bigger than some A0, then the solution exists globally. And what's the term of a weakly mixing flow? So if we have vector field U and you generate some one parameter family of diffeomorphism or automorphism from torus to torus, meaning the X. We saw this equation many times in this talk. And here, X. And this phi of t, actually U is, if we assume U is ellipsis and domain is compact, then this curve exists globally. So phi t gives some automorphism forever. Okay, and so with this phi t, if we can write the density equation. We can solve the density equation by reversing the trajectory like this. And for this, we can see the operator from n0 to other function for each t. So we can define the L2 operator, L2 to L2, by any function 1. And this is called Koopman operator in dynamical system community. So what is a weakly mixing flow? Is that type 1 flow, type 1 operator U1 has no non-constant eigenfunction, then U is called weakly mixing. And in L2. So actually, Constantine's paper, they construct some H1 eigenfunction. But the definition is that no non-constant eigenfunction in L2. Then, okay, what's good with that weakly mixing flow? And it's a theorem called Ray's theorem. And applied in this case, the theorem says that T is very large, then the T U F L2 is small. So we should read this theorem as the sigma is given and F is in compact domain in L2 unit L2 ball. Then and N is fixed for any N, for any sigma, for any F, for any N, and the Pn is the Littrow-Pelly projection, the lower frequency space. Then we can find some T0. So if T is larger than T0, then we can estimate this term very small. And what's good with the A was the role of parameter A. If we A here, then U, and it affects the theorem here, T0 divided by A. So actually T0 can be very large, but if we increase A, then we pass the condition for sufficiently small T, because the A is bigger than T0 divided by S can be small. Then the smallest will help to estimate in energy estimate. Always we have from the dissipation. So we always have this norm with good sign, and then here in this parabolic elliptic case, maybe this norm. So the idea is that if the homogeneous overlaps norm is sufficiently bigger than L2, then on the left hand side, here the time derivative of L2 norm. So if we can somehow manage this sign by negative, then what's that? N L2. Actually, this is LT infinity less than initial value. So and it's not very difficult to cook those ingredients to make some continuation argument for global existence. In this way, they can show the weakly mixing flow and a very big A, then really suppress the blow up. And also they can show the mimicking the R2, mimicking the argument in R2. They can prove without this A, without this term, the solution. They can find there is solution which blow up in finite time. So, and the problem is that I asked, so how many weakly mixing flow and how stable? But it turns out that I posed the wrong question. I mean, I should ask how generic of the weakly mixing flow. And actually, I found some materials, then it's not very typical. The vector field is weakly mixing. Even it's incompressible fluid, so always a volume preserving, but it's not sufficient. Weakly mixing is really, I don't know. So, well, okay. I stop here. Thank you for attention.